This is part 2 for the topic Steady Electric Currents. And in this video, we are going to discuss about conduction and convection currents. In electrostatic situations, the electric field is zero everywhere within the conductor. Therefore, there is no current. However, this does not mean that the free electrons inside the conductor are at rest. In fact, the free electrons in an isolated conductor are always in a very random motion, even at room temperature, with individual velocities in the order of 10 to the 6 meters per second. But due to the random motion of the free electrons inside an isolated conductor, there is still no net flow charge in any direction, hence the absence of electric current. However, if you place a battery between the terminals of a conductor, an electric field will be established in it, which will exert a force on the charges, causing them to move. And this movement constitutes the conduction current. The directional movement of charges in response to the externally applied electric field creates a drift velocity. For conduction current, the battery does not supply the electrons, but instead, it only establishes the electric field that causes the electric charges to flow in its directional axis. In the presence of an electric field, in spite of all the collisions, the charge carriers slowly move along the conductor with a drift velocity v sub t. Although the individual velocities of the electrons are extremely high, the net drift velocity is small due to the collisions with other electrons. Let's consider a segment delta x with charge carriers q moving in its direction through the cross-sectional area A. If there is n charge carriers per unit volume, the total number of charge carriers in a given segment of the conductor is n times the volume of the conductor, which is A times the length of the conductor, delta x. The total charge in this segment can be computed by multiplying the number of charge carriers present and the charge of an electron, denoted by Q subscript E. By manipulating this equation, we can come up with a formula for the average current, or average conduction current, which is Q subscript E times N times the area A of the cross-section times the drift velocity V sub D. Convection current is produced by the motion of charged particles in free space, where free space is a region void of matter, and hence convection current is not electrostatically neutral, and it does not require a conductor, and it does not obey Ohm's law. For a steady current, the current passing per unit area must be the same. Thus, the velocity of the charges increases, the charge density has to decrease. This will be illustrated in the succeeding slides. Let's consider an incremental charge delta Q, which can be expressed as the volume charge density times the incremental volume. By substituting the dimensions of the region for the incremental volume, we can get another expression for the delta Q. If the incremental charge is moving through the length of the region, delta x, we can derive an expression for the incremental current, as well as the current density in this region. Generally, the current density J is the product of rho sub V and the drift velocity. Again, conduction current requires a conductor, which is characterized by a large amount of free electrons. Thus, an electron will suffer constant collision with the atomic lattice and drifts from one another. there will be loss in momentum for every collision, but there will also be an increase in momentum due to the applied electric force. In general, the force measures the rate of change of the momentum. Whenever an electric field is applied, the force on an electron with a charge negative E multiplied by the applied electric field E is the force on the charge, as shown in Lecture 1. However, the force, or the rate of loss in momentum due to collision, is given by the ratio of the mass of the electron times its drift velocity, with the mean time per collision, tau. So under steady-state conditions, these two rates of momentum is equal. So as stated in the previous slide, the rate and the loss of momentum must be equal to the rate of gain of momentum. So we can equate the two expressions for the force, or the rate of change in momentum. And we can compute for the drift velocity of an electron in the conducting medium, which can be seen to be proportional to the applied electric field. The concept of proportionality is called the electron mobility, denoted by mu subscript E, with a unit of squared meter per volt second. The drift velocity is in meter per second, and the negative sign only indicates the direction of the drift velocity, which is against the direction of the electric field. The formula for conduction or convection current density can be used to derive the conduction current density by substituting the expression for the drift velocity of an electron in a conductor. We get the expression for conduction current density J as the free electron charge density rho sub E times the electron mobility times the electric field, with J being positive since the free electron charge density is negative, thus canceling the initial negative sign. For a linear medium, J and E have the same direction. The concept of proportionality between J and E is called the conductivity of the conductor, denoted by sigma. Sample problem number 2 for this topic will be solved in the next video.